back in my real days, back in the 80s. We do that stuff. My name is Tammy. I'm with USGS Astrogeology. And Chris Becker is leaving for some reason. His name's on here to help me out. But so I'm here to discuss ISIS 3 and introduction. I see a lot of friendly faces, hopefully some new ones. And I'll cover a little bit the basics in the beginning, and then we'll go into what we've been doing more recently as well. So ISIS, in order to process planetary data, we've been doing it for years, 30 years. I've got pictures up of the Voyager Viking days where we were making controlled base maps during PEX and ISIS 2 days. Galilean satellites, Galileo mission and Clementine have come along, but we've been processing planetary data in this environment that we're going to discuss today for quite some time, as well as sharing it with the community. We have well over 300 image processing applications. The emphasis is on photogrammetry and sensor models, cartography and map projections, adjusting and improving the SPICE, and basically generating foundational data products for the community and for missions. We currently, as of today, support 68 NASA ESA instruments, all ranging from framing cameras, line scan, push frame, and our special cases, radar instruments like LRO Mini RF, and spot instruments, Cassini bands. And by target, we have the instruments listed. It's quite a list. It includes a lot of the legacy missions that we continue to support, newer missions, approaching asteroids and whatnot. I have asterisks by camera models that we're still working on, but they're close to being complete. So in terms of an introduction, I wanted to share our user resources. Most of this PowerPoint is meant for you guys to be able to print out and take home and use. But there are a list of our sites of information, our installation guide, online workshops, command line options. So just your list to pick from there. Our current ISIS 3 status, our most recent release was in January. We have a new one scheduled for late July or August, and our list of OSs we support. We are posting most of our information on Redmine. This is a snapshot of the front page. Make sure that you select ISIS as the project, and you will see the variety of information that's available, including issue tracking and latest news. If you select news, you'll see the same information and public release information, including your download installation information, as well as parameter changes or anything that's you need to know, of course, with the recent release. We have training tutorials available, as well as posted lessons. We hosted and conducted a hands-on workshop last summer in July, where we processed HiRISE, CTX, and Themis data. We have all those lessons available on this location, as well as the online tutorials that explain in detail what an ISIS cube is, what are special pixel values, what are map projections, and a lot of planetocentric, planetographic, how to process Cassini, how to process HiRISE. So those, hopefully you'll find useful tutorials to get through. Is my mouse showing up? There it is. One useful part of Redmine is the issues. You can post questions, recommendations, feature requests, bug reports. We do ask that you search for your issue. It might have already been posted and being addressed. Might have been answered. There's a search area at the top that you can enter CAM to map, and you might it'll come back with a list of tickets that we that involve CAM2MAP. If a ticket does happen to reflect your issue or your idea, you can add a note to that ticket. You can add yourself as a watcher, so if there's any changes or modifications to that ticket, you will be notified through email. Of course, if you don't have or can't find an existing issue, you do have to log in. I don't think it's obvious at first, but you do have to log in order to see this new issue that you can select and create a new ticket basically with your information. The more information you supply us, of course, the more we can help you. That includes where you, what data you're working with, the commands you were using. Sometimes that's lacking and we have to kind of poke back and ask for more information so we can help. So we just encourage all the information possible. So back to introduction, what does ISIS 3 do? So the fundamentals or the foundation of ISIS. ISIS expects and supports PDS archive data. PDS obviously supplies the community with standard keywords that will tell ISIS what mission, what instrument, what target body that your image of interest is. And with the NAVE toolkit, of course, is what I would consider the heart and soul of ISIS. Combined with this PDS image, ISIS incorporates those together so that at the time of your image, it can tell everything about your image. Of course, a foundation as well as this camera model to understand the camera that you're processing. The target body, shape model, your local topography, all those are foundations. And I've got a little user guide. He's holding the Earth, but it could be anything. Of course, I think we don't process Earth. Anyways, you have the applications built on those building blocks so that you can learn and process your data to your heart's content, of course. Sometimes not easily, but ISIS, every single application in ISIS has a GUI interface. You'll recognize in the icons in terms of opening files and running. We have a help that you can select, and it will present to you all the documentation of that application. We have a little "What's this?" button that you can hover over the parameters presented to you to learn what might be more information about that parameter. There will be radial buttons that are already selected for default, and the results will display in this little portion of the GUI below after you run your application. This is a simple utility program, stats, that computes statistics of your pixel DMs of your image. An important note, any GUI, the GUI reflects the command line format of how you're running that application. I don't think the default parameters show up because they're not necessary if you are leaving them as default. When you change from that default, you'll see that parameters show up with your override. Within our documentation, we try to link terms that you'll frequently see throughout the documentation. We try to link those terms to a glossary of what that term is referring to. The command line option of ISIS is very powerful. It's what actually helps support the pipelines that LROC and HiRise have used, because you don't have to go through the GUI, of course. But the command line options, we have a link to all the options with the command line. But in this case, we have the stats application. And if you do not know the parameters offhand, this is what I frequently use with the dash help. It simply displays the parameters for you. And the asterisks indicate the default. And that's how anyways, so you can see the parameters. And then you can fire up the web help with the dash web help or the GUI itself. You can actually, like I will often have long file names. I can say stats from capture a copy paste of the file name. And then I might not, want to see the parameters, of course, through the command. So you can say dash GUI and it'll fire up what you loaded into the parameter from the command line, and will show up the GUI. The batch list command is a nice feature. You can create an ASCII file of 10 file names and run stats on 10 file names with this batch list, and the $1 picks up every line in that file, that list, and just executes stats for you. Back to what we're doing with ISIS. I have an example of camera observations of Mercury during the M2 flyby years ago, actually at this point. But it's as the spacecraft captured Mercury in 9 different frames. I think this is the NAT, or no, it's the WAC G filter, sorry. And so ISIS basically is built to, you ingest these camera level 1 images, and they can be radiometrically calibrated and map project them into an equirectangular projection. This example has them, I've specified the output map characteristics to be the same resolution and same center longitude for all of these images, though ISIS will default to whatever it computes for each individual image. Anyways, this is one of the most fundamental things that, and most common use of ISIS, is projecting your images. What is a projection? I'm going to kind of deviate from steps and more into concepts of what ISIS is doing. But when you project your images, you're basically taking your images of a 3D object and projecting them into a 2D plane. And ISIS offers a number of projections. I don't know that this is the entire list, but these are the most common map projections. We have a tutorial about projections on the red line. And we have map templates. Each of these projections have different requirements, whether center longitude, center latitude, parallels, resolution, things. And so we have map templates for each of these projections that you can refer to. And there's a nice USGS map projection link that kind of can tell you what projection might be useful for your data. Obviously, when you're at the South or North Pole, you want to explore and try and get polar stereographic rather than a sinusoid for obvious reasons. But this website shows you the advantages of each projection. I didn't want to go into this in deep detail, but just wanted to point out that when you are map projecting your data, you are picking up the pixels from the original images and interpolating them and moving them to this 2D space and this map projection space. Process that's involved. And ISIS 3, the CAM to map application, defaults to the cubic convolution, which it almost filters the data, and it's a nice, smooth transition. And we prefer it for mosaics and images. But if you are projecting your DEM data or spectral data, you don't want that smoothing to occur on the output of your projection. So by nearest neighbor bilinear would be the option you would want to select for CAM2MAP. So I just want to point that out to those who might not be familiar with what's available. The thing that I always repeat, when you are in ISIS, it does default to certain map characteristics, and that would be the planetocentric system. If it's a sphere, of course, they're equal, but just know if you are projecting, you let everything default, it's going to project your output map to planetocentric. It will be east, and longitude domain 360. You can override those, of course. When you select a map projection, you can define those output map characteristics and override any of those defaults, but just know that that's the default. CAM2MAP will compute the pixel resolution for you, the latitude, longitude range of your image, and a CLAT CLON. Again, you can't overwrite those. And you have to when you're going to mosaic your images. The example that I had shown with the messenger images, they were, in order to mosaic them into one map, they have to have the same projection, the same exact map resolution. They can't even be off by anything behind the decimal point kind of thing. the same center lat, center long, and the same wavelength of band, which you can override. But just know if you want to mosaic your images together, we'll often get support questions, why isn't it working? And that might be why. And so here's an example of those 9 images mosaic together in equirectangular orthographic and sinusoidal. One thing about ISIS, going back to the building blocks with SPICE, and I deviated and went down the path of map projections, but all that's possible because, and that occurs in the camera space. So the minute you run SPICE in it and you have a successful SPICE in it on your image, it'll compute anything it needs to for every pixel of your image. And this is a demonstration of the footprints, the commands you would run SPICE init, footprint init, and CamStats. And we have this application called QMOS, which will present for you the footprints of your images in an equirectangular or a choice of map projection. So you can see at least where they overlap one another without actually projecting and moving the pixels to compute those polygons, and then QMOS presents them to you in your choice of projection. This particular application is one of my favorites. This view of footprints does interact with your list of images. You can have hundreds of images, and you can bring forward, backward the layers of footprints and identify who's who. There's grid options. So I'd encourage you to play with QMOS. It's a useful application to know your data, get familiar with your data. CamPT, CamStats, CamInfo, these are all utilities that will report back to you about every information that you would need for every pixel and every image. A lot of folks will use these to build PVL or CSV files to incorporate into a database to search if you have large amounts of data. CamPT output, here's an example of ground point for a certain sample line, defaults to the center of the frame. TU, the latitude, longitude, and no center go graphic, and your longitude east and west, your solar information, your photometric angles, and time. This can be handy with a high-rise image or such if you want to know the time of a certain line of your image. CamPT will, you supply it that line, and it will come back with what time that line is in high-rise. I'm emphasizing again the coordinate system that ISIS defaults to in terms of the longitude domain being 360 and positive longitude east and planetocentric. Cartoon basically of what your photometric angles are that ISIS computes, again at every pixel, your emission angle, incidence angle, and phase angle from the surface normal. This actual cartoon shows off an ellipsoid. You notice that there's no relief on that little target body there. We'll talk about that in a minute. One of my favorite examples is the wide angle Enceladus image on the left. And there's a program called FOCube that produces a latitude, or it has about 20 options of what to compute for you and actually create an output cube of latitude. This longitude, actually, example of this image crossing the 0 to 360 boundary. And your incidence angle, your subsolar point being around here, mission angle, your subspacecraft point at the darkest, the range is 0 to 90 here, and the phase angle. And our 9 little Mercury images, FOCube can be run either in the raw camera space or in your output projected space for each image. I actually, I think I ran FOCube on the individual projected equirectangular images and then mosaiced those backplanes together. So we have your mission angle and incidence angle and pixel resolution. We get another occurrence where we're crossing 0 to 260. A little more cartoons. The heart and soul of ISIS. It's all possible because of the SPICE, like I said, and our sensor model. But basically, in the most simplest terms, pixel position in your image, ISIS will intersect the target based on the spacecraft look vector and center of your target body and report back to you the latitude, longitude, and radius. It is performing CAM PT, CAM stats for every part of the image. Again, you see that it's a sphere. If we add a DEM, a digital elevation model, which ISIS does default to LOLA and MOLA for the Moon and Mars, that latitude and longitude reported back to you considers that local topography. So that latitude and longitude actually would be different, of course, than what's reported on the sphere. One of my favorite examples with the use of the DEM, when you map project, using that local topography to compute the latitude and longitude, there's an orthorectification result. And the far left image is an LRO mini-RF observation of Shackleton at the south pole of the Moon. With the radar distortion, your bottom of your crater is distorted to look at the rim of the crater. And projecting it onto the moon without relief. I project for you, north is top, north is at the top, and that it did not consider or even know that you're projecting a crater, obviously. So with the use of the DEM involved with the projection, that crater is, the bottom of that crater is now recognized with the relief and map projected more accurately. Another example, ISIS, when you map project your images, AutoMOS, the program that mosaics the images together, has an average option. So wherever the images overlap, you can actually average them. And we do frequently use this option in Mosaic to how registered our data are. So when your SPICE is inaccurate, your craters are not going to map to the same exact location on the surface. And that's our job, is to adjust that SPICE so that they do overlap. We're at the same place on the target body. So on the far right is our worst case scenario. The red dot in this illustration shows the same feature. It's the same stack of images, mosaics, and averaged together. Keep losing my cursor. So the far right has the a priori SPICE, which shows the inaccuracies. You see the ghosting of the craters mapping to different locations on the target. And when they're averaged together, that's where you see the ghosting without a DEM. The next one over is remains uncontrolled, same a priori SPICE, but with the relief accounted for. So you can see a slight improvement in that registration with that orthorectification in place. Of course, then you can control your data and you actually adjust the CK pointing, camera pointing of the images with the attempt to converge those features at the same lat long on the target. But when you map it to a sphere without accounting for that relief, you still see the offsets. So then at the far left, you can see that sweet spot of having registered data registered to the DEM as well. And that average actually shows all the images lined up. Now that we're talking about the DEM and the shape models, I think we've all heard about the new DSK, and we've implemented it in ISIS, I think well over a year ago. And just comparisons between the DEM and the DSK. A DEM is actually the absolute radius values in meters, and you can actually display it as an image. The DSK you cannot. Just that format obviously is not very easily to just treat as an image. It's not an image. But there is a program called DSK to ISIS that does allow you, I think, that's magic. I'll let somebody else in the room talk about what's happening. But you can actually display the DSK in that manner. Obviously, for bodies like Itokawa, the DSK is a must. When the DSK is actually kind of a new concept to myself, and as we were implementing it, we were testing it, and we found this one image of Vesta. It's a oblique view of the South Pole. On the left is the original image, and my command to run spice init, and I'm telling it to use the ellipsoid Vesta, so meaning no topography. Uh-oh, wow, I think I've got like 20 more slides. Okay, one useful utility program called FX will compute the local radius for every pixel, and so that's what the lower right output is. And then I asked FOCube to give me an emission angle and a local emission angle. And so you can notice that as we head towards the limb, our values are near 90. And the radius, whatever that means, but it's all nice and smooth. But notice that the line of where it thinks the edge of the body is not, it's actually trimmed from where the relief above the Vesta radius is. So we actually lost data in the sense of where ISIS thinks the edge of that body is. Okay. There was quite an improvement. So you can see that we were able to retain and see that relief above the limb. And the local radius, or the local emission rather, when ISIS computes the emission angle, it actually accounts for the slope of the topography. So a local emission angle slope versus just the regular emission angle. Okay, back to basics. Wow. Okay, so there's a flow chart of what we just talked about. Something that we don't document really well are user preferences. So I included this for your home reference. Anything about how ISIS operates in your environment. Anything you apply onto an image goes to a history. Anything you run in ISIS goes to a log file, print.prt. You can turn that off in your ISIS preferences. There's your print.prt, we're fine. ISIS has a convention of applications when you ingest from PDS. The prefix is emission and instrument. That's very, very important. You can't just go out and download a PDS image and say PDS to ISIS and expect things to happen. ISIS has to know what mission the spice init needs to know to load those kernels. We do have general import programs. Here's our list. No, we always encourage you to know your data, CAMSTATS, CAMPG, QMOS, get familiar with the data you've ingested. And more tools, and there you go. There's Enceladus. I wanted to share with you what we've been building in ISIS lately, what we can do. You start with your collection of images, you build a control network, you adjust your pointing, and you make a mosaic. It's that simple, right? That's simple right there. We've worked with Themis data. We have controlled nighttime IR, daytime IR, Apollometric, Messenger DEM. A nice little picture of before and after the MDIS control with the DEM. The images on the colorful image is showing the count of images of average up to 160 images are averaged in this product towards the pole. Before and after. This is why we want to control our data. Sorry, I'm flying. Viking. CTX and Viking. It's all lined up. Recent R&D, we use Pixel to Map. We've expanded its functionality for field of view. This is Dawn Beard Vesta data, so we actually map project one pixel at a time rather than the entire image. It can be very useful when your images are not lined contiguous on the surface. Polypan sensor model is almost there. Rosetta, Osiris, NAC, and WAC. Map occlusion, I really wanted to talk about this. ISIS needs to know that it can't see the bottom of the crater, so why is it filling it out when you map project it, right? We're working on that, especially with bodies like the Chicago where you've got occlusion of the whole body shadowing itself. ISIS should not be filling in the gaps. Minor, really powerful tool. I encourage you to check out. Stereo pair ranks are computed from ISIS Minor. Oh gosh, Chris Becker went over the new control process the other day. Some spice functionality, I think that was touched on the other day. We actually, the red dot shows where, how registered the Kava data is after using some spice to align the spice. So sorry. I think some of it.
Totally have time for a question if there's some questions.
Oh, come on. Oh, good. Okay, good. I thought you were leaving.
Maybe you've said, hello? Yeah. Maybe you said it, but do you have to input the spice kernels yourself, right?
No.
They are built in.
Yes.
What about if you want to load other kernels? Because sometimes, for example, at least for the NAS emissions, typically you use the ones which are archived
Yes.
in PDS. But for EASE emissions, those archived in the PDS usually are not the most up-to-date ones, at least right now, and it's my fault, by the way.
Understand that. I have experts in the room that are going to answer that.
Basically, has options in it where you can specify CKs, SDKs, and even additional kernels that you can specify runtime. So there is a good interface that allows you to specify those kernels directly.
Actually, real fast. I was going to go back to the Vesta image, my spice init application. Yeah, so see this command where I actually specify extra because we had a different prime meridian and all that about Vesta that was not in the ISIS default system. So I overrode what I needed for Vesta at that particular moment that was consistent with the Gaspol DSK kind of thing. So yeah, so there are options to do that.
So basically you override, what is that?
You think it's command line will override.
Thanks. Very good, by the way.
Oh, thank you. Thanks.
Yeah, I have a question. So are there plans to expand the functionality of the Spice server? Because like I use a stereo, so there's a few commands where I think like Spice initting, like some of the data, I think like that can just use the server, but there's some later commands that are called that have to have a full MRO kernel pool for the things I'm working on. So I'm curious to hear if there are plans to expand that so it's toolkit wide.
Yeah, we recognize that a lot of the radiometric calibration applications require, I think, a kernel to be local. And so when you use the web server to get past Spice init, then what is it, high cal or something says, oh, wait a minute, I want to know how far Mars is from the sun to do this. And then it wants the kernel. So we recognize that, and I think there are plans to decouple needing that kernel and actually use maybe what's on the labels when you calibrate. So that is a known issue.
So
I suppose like
next up, sorry to interject. Next up, we're going to get Ken Edmondson setting up. Maybe while you guys finish close out this question.
Keep talking, yeah.
So we're in the process of designing a RESTful interface for Spice that ISIS will use, but will be available to others as well. It's probably not going to be available for at least a year or two, but we're working on it.
Good question. Oh, wait, I'm taking me with me, aren't I?
In fact, if you have a USB,
Yeah, I'm trying.
Okay. Semi-happy now. My name is Ken Edmondson, and I'm with the Astrogeology Science Center. And today we're going to be talking about a relatively new ISIS program. Actually, it's been in development for some time. Was that?
More volume.
More volume.
How do we do that? How's that? Yeah? Okay. And I'm citing a relatively new ISIS program called the Integrated Photogrammetric Control Environment, or IPSE. I think it was actually listed in the program as the Integrated Planetary Control Environment, which is wrong on so many levels. Tracy Sukarski is the lead developer. Wave your hand on this. Of course, it's been more than just us two. There's a host of people that have been involved in this development going back quite some time. Some are retired, some have moved on to other jobs. I think a lot of them are actually in the room as we speak. We're going to show you the software, assuming stuff. But before I do, I've got just a handful of slides to give you an idea of the motivation behind why we even went here. So, I think it's awesome that there are now relatively inexpensive, commercially available photogrammetry packages like PhotoScan Pro, so that now you and your grandmother can do photogrammetry. But it's really difficult to black box the photogrammetric process. It's a worthy goal. We're trying to do it to some extent, but you're never going to completely do it. Something always goes wrong. User intervention is always required, and when something does go wrong, it sort of helps to have a knowledge of what's going on in the background. So, in an effort to protect my job, and speaking for photogrammetrists everywhere, I'm here to tell you that photogrammetry is hard. Well, I don't have to say it, but it's fun. It's always fun, except when it's not. How many people in here have actually used ISIS to do photogrammetric control, not including astro people? Okay, so that's actually good. Photogrammetry, maybe I should sort of define it very quickly. Basically, we're measuring things with cameras, right? And no matter what you're measuring, the math and the process it's the same, regardless of whether you're standing on the floor in Boeing, taking pictures of an airplane for quality control, whether you're mapping an archaeological site, whether you're using a drone to map a lava flow, or whether you're doing the stuff we're talking about doing here, which is creating mapping products, images, digital elevation models, digital image mosaics. It's all the same. You may be looking for different things. If you're at Boeing, you're looking for dimensions. If you're mapping a crater, you may be interested in volumetric information. If you're doing our stuff, you want to make mapping products. Regardless of what you're doing, it's critical to know where the pictures were when you took them and how they're oriented when you took them. And for us, that's primarily defined by stuff we get from the missions, where the spacecraft was, how the camera was oriented when it was taken. SPICE is never perfect, ever. and errors in SPICE will propagate through the photometric control process to the final products, and you might get something not quite as desirable as you would like. Like the messy mosaic on the left there. So the process, in effect, is to refine the SPICE, to make the SPICE somehow better. And how do we do it? Well, Tammy said it. It was easy. It's easy. We measure images, and we register images by measuring features that are common to overlapping images. We may measure control points on the surface, features that are common between images in, say, base maps or digital elevation models. In the case of the moon, human artifacts, landers, rovers, retroreflectors. And then these image measurements, along with whatever values you have for SPICE at the time, go into this big old fancy that we call the bundle adjustment, and we run it, and if everything goes nicely, what comes out are better values for the SPICE, and then we can use those to make prettier mapping products. Well, I guess Tammy was right. It's just that easy. 2 steps, and we're done. I wish you were so. In ISIS, there's over, well, this is out of date, roughly 30 standalone applications that are part of the photometric control process. So you start an application, you start processing some data, you get some output, you take that output and feed it into the next application, and get some output and feed it into the next, and maybe you've got to write some stuff down in a notebook along the way about that. Well, there's too many standalone applications. It's error prone, it's inefficient. I said photogrammetry was hard. That's true. The underlying applications are hard. Feature extraction, image matching, bundle adjustment, outlier detection, that stuff's not easy. We really don't provide enough tools for the user in ISIS to analyze the data that comes out of these different applications. And the simple fact that we're running all these standalone applications really limits the potential for automating the photogrammetric process. And so we're trying to make it better. That's the whole point of this presentation, the whole point of IPSI. We're trying to bring most, if not all, of the functionality in these existing ISIS applications under a single interface, IPSI. We had hoped, I think, to get this out to the public this year, but it's probably going to be next year. We do have a prototype internally that's being played with by our users, and our development team's getting feedback in this development. And that's what we're going to show you now. This is a work in progress. What it looks like today probably won't be what it looks like when we show it out to the public. So here we are in our shell, and I'm going to just start it up. And you can see straight off the bat that the interface looks a whole lot like any other Windows-based program. We've got a project tree on the left with nodes to hold the data that you're going to be working with. We've got in the dark gray area basically a place for different views of the data. And down at the bottom, you can see warnings and history and progress boxes. And another caveat here, what I should say is that what I'm going to show you is basically starting from the premise that we already have a control network, which is sort of lame, I admit. Ideally, we would like to go into this project. You've got nothing but images, and you use a automated process to start to control that. Whether it's something like the existing processes in ISIS using auto seed, seed grid, point reg, or whether we're perhaps implementing Chris Becker's find features or some elements of J or its auto CNET program, which he's going to talk about in a little bit. Eventually, we're going to implement that kind of automation into this program. We don't have it yet, so we're starting today. An existing control net, you're bringing it in, and you're going to do some editing. So that's what I'll do. I've got a very, very tiny little Apollo 15 project. Somewhere.
Go back up. Go, you're lost.
Yeah.
Go up, keep going. Like, select Apollo, nope, no, back up. Apollo, don't double click, choose
Oh,
Apollo.
Oh, gotcha.
No, no.
Where am I?
You are lost.
Start from scratch. Okay, I don't know how to use my own software. Okay, we can import images using a list. We can import the directory directly. We can import the cubes directly into the project, or we can say no and don't, and then the paths to those cubes will be stored. I'll go ahead and import them in. And you see at the bottom that the progress bar is showing what's happening. So now I've got images in the project. Now I'll import an existing control network. And there it is. I can import a shape model, in this case a 2.5D shape model as well. Since I'm lost again. Okay, so now if you look at the tree, you see we've got a control network, we've got 4 images, we've got a shape model. The control network's tagged in green. It's right now the active control network. We can look at it. And if you're familiar at all with anything in ISIS, you know we've got a program called CNET Editor, and this is effectively what that is, which allows you to view the resolution's not the best here, but it allows you to view the control point information and the associated measures with these control points and various other views onto the data. We can display the images themselves. And there they are, or at least one of them. Yeah, that's not good. There we go. And you see, because we have an active control network, that the measures from that control network are actually overlaid on the images. We can also display the shape model. And when the images were imported, the information on the associated target body comes in as well. So under the target body, you can see the moon, and we can see information on that as well. Same with the instrument. Not totally filled in at the moment, as you can see. And so we can see our data, we can see the control network, we can see the imagery. We can also see the footprints associated with this imagery. And I can import an existing map file if I want to change the longitude domain. I can overlay the control points from the active control network on the footprint view. So now we're up to this editing of the control network part. And we can do this from 3 places. We can do it from the footprint view, we can do it from the images themselves, and we can do it from the control net editor view. So if we're in the footprint view, we can select the control net icon, which actually is already selected. Hover over any of these control points, you get a little pop-up that displays some information on that point. If I left click on this point, we go straight to a control point editor window, where we can, again, this is like an existing ISIS application, QNet. You can manually edit this point, this measure, I should say. You can register it. And you can see that in this case, there's 2 measures associated with this particular point. And I can also make a new control point if I want. If I look at my footprint view and I see, wow, there's a place here where I'm a little bit slim on points, I can right-click and create a new control point. And we immediately are in the control point editor. Once again, with this new point, we know which images overlap this point. We can go ahead and refine this point from this location. We can do the same thing from the DN view, the QDN view. I can select the control point editor tool. I can, same thing, left click on an existing point, get the control point editor. I can right click in an area where I have no points and get a new one. And proceed to edit it. And I can do the same thing in the control net editor view. I can select a point here, cell highlighted, right click, say edit the control point, and we're again in the control point editor. So we have a variety of ways that we can edit these points. Now let's assume that we're happy. All our stuff's been edited. Now remember that next step after you've measured is to run a bundle adjustment. We can do that in here as well. So we bring up our bundle adjustment from the project main menu, and what you're seeing is not too dissimilar from the standalone Jigsaw. Much of the many of the options from there are here as well, plus more. And some of these tabs are not functional at the moment. For example, self-calibration, we intend at some point to be able to actually solve for camera calibration parameters, focal length, principal point offset, lens distortions. In this case, we're not going to do that, but I will just make some selections on things I'm going to solve for in this incredibly tiny network. I'll solve for radius, I'll do rigorous error propagation, change our convergence criteria. I'll solve for positions, and now I probably want to put some sort of a priori weighting on these parameters. So since I've done this like in my sleep, 500. Oh yeah, resolution problem. I don't know if you're familiar with METs. Those are meters and degrees on the angles. So that's my setup. I say okay. I run Jigsaw, and it's really small, so it's really, really fast. And I get some kind of result, which I can see some statistics in this box that come out. I can see a sigma 0.6. That's a function of the residuals. And I can perhaps, if it looks terrible to me, I can reject it. I can accept it. Maybe look at the results. Maybe I know right now I don't like it, and I want to go right back into setup and tweak something and run it again. And also I can, let's say I've got a massive bundle adjustment that's going to take me days to run, which I can only just emulate here by increasing my convergence criteria to something ridiculous, and then run it. And you see it's just going to go until 16 days, and I'm like, wow, something's really wrong here. I can abort it and choose to revisit the settings. The bundle is threaded, so when it's off doing its thing, the GUI is still available. You can go off and do other work while the bundle's happening. So let's reset to a more reasonable convergence criteria and run it. Now, keep your eyes on the project tree over here. So I accept it, and you see under results, under this particular runtime comes the results associated with that bundle run. So you see the settings that were involved, the output network, statistics associated with that result, and updated, in this case, these are updated detached labels. from that bundle adjustment. And I can still keep up some of this stuff, and I can, for example, have a look at some of this, some of the output. There's the measure residuals, and I can sort and examine and use that information to help me go back and edit more if I have to. I can look at statistics on the images. I can look at statistics on the control points. And maybe already I know, I screwed up. I really should have weighted my spacecraft positions a little differently. So I can go back in here and tweak that a little bit. Say, okay, run it again. I've got a new bundle. I accept it. And you see it shows up again. That particular result shows up on the tree. Now, again, what's happening is that we're not duplicating the cubes themselves. We're only setting out the attached labels associated with those cubes with updated spikes from the bundle adjustment. So the idea is that you can bundle, day in and day out, and you can have numerous bundle results on the tree, and you would like to be able to compare and contrast them in various ways, and you can do that right now through examining statistics. And the question is now, what do I do with this stuff? Now, looking at the statistics is critical, right? But in some ways, the final decision, the final evaluation of quality is going to come from creating a mapping product, creating a mosaic, and having a look. Sometimes you can be deceived. Sometimes the bundle looks just smoking hot, and you make a mosaic, and something wasn't quite as hot as you thought it was. So the fact that we're spitting out detached labels for each one of these runs means that we can create products using those labels and the original still that was imported into the program. So, for example, and by the way, we did this like at 7 o'clock last night. I can right-click on the images that came out, the updated image list that came out of a particular run, and I can right-click and say, create a mosaic. And we can't see the progress bar here, I don't think. But it happened. We made one. There's a thing on the tree down here called mosaics, and there's mosaic.cube. And we could, if we want to compare and contrast this, I can do it with the second bundle run as well. Make a mosaic. Hopefully.
Need to go to import.
Might hung myself up.
Import 10.
Yeah, I got you. There we go. And now we got two mosaics. They're both the same name. And to be clear, for the demo, we sort of just made this happen really quickly, real quick and dirty. Not that there's times when you don't want to just make a quick and dirty mosaic to have a quick look, but clearly the thing that's missing that we'll do next is to implement the capability for the user to have full control over that process, to control how images are projected, to control how the mosaic is created, to control what selection of images you want to use to make the mosaic. And now we can look at these mosaics. There's one. There's the other in the same view. Surprisingly, they look exactly alike. And that's it, almost. Another thing I wanted to show, because I had said that in our bundle adjustment stuff that we were solving primarily for spice position, attitude of the imagery. We also get out the triangulated coordinates of the control points that are involved. I mentioned that we maybe I mentioned the fact that we have implemented the possibility of solving for target body parameters. So spin axis, pole position, prime meridian offset, and again, eventually we're going to incorporate camera calibration parameters into this as well. And I have a link. An existing project. Now, this is just a portion of an Enceladus network that we ran last year, I think it was, with nearly 600 images. I've only got a handful in here because I'm not going to run the bundle adjustment for you. What I am going to show you is that we show here the right ascension declination, the pole position, prime meridian, and the triaxial radii for this bite is coming right out of the PCK. And if I wanted to show you the bundle adjustment running, and I wanted to solve for those parameters, I'd go over here to the target body tab, and you can see I have the option of solving for all of those things I just mentioned. I can select right ascension, declination, prime meridian offset spin rate, and then I could give them associated a priori uncertainties, and then go for my life and solve for that. And as I said, we did it. And if I can get my slide back, I'd show you. That's not going to happen. There we go. That's a slide showing the final results of our 580 some images. So lots of stuff still to come. Again, what you're seeing is a prototype. I already mentioned that we're going to add more automated image measurement techniques, 3D visualization of just about everything, including adding cosmographia into IFC. Lots of stuff on the horizon to improve the bundle adjustment, including, as I said, self-cow, free-net adjustment, and whole bunches of other really cool things. And that's it. There's probably no time for questions.
We've got about 2.5 minutes for questions.
2.5 minutes, just in case. Anybody? All right then. Oh, wait. Okay. I knew this was coming.
Danny Della-Justina, U of A. So just two questions. They still to come, but what is the timeline that you guys are trying to follow to get this out into the public release devices?
Hoping FY18, early FY18,
Okay.
to get something out there. It's probably not going to be fully functional, but as I said, we're working with our internal users to iterate on getting this up and running.
Great. And then you mentioned that you can import 2.5D shape models done.
Yeah.
What about 3D tested shape models?
Well, we obviously intend to do that.
Okay.
Yeah, no doubt.
All right. Great. Thank you.
Yeah.
We're going to take a break for a couple minutes, and we'll be back at 3:15. I think, Ross, are you doing the demo, or Ross in your group? Cool. For AIM stereo pipeline demo.
Maybe we can get but not.
We have functionality that's nice, update the SDKs and see this is going to get incorporated into this project.
But as you mentioned, for example, it should be, I'm not so I lack of them know that everything that has to be done, we need to know the process. But let's say that I wanted to take a look at this how, I mean, did I find my way to do it just by looking at the sources, maybe asking some people from the
Hang on. Absolutely. Yeah, this particular, I mean, you can do an ISIS right now in town. With this particular software, you're going to be able to do it as well. Today, this is a really prototype program, lots of issues. Yeah, of course. Yeah, absolutely.
Like a Q&A.
Didn't feel good.
Did you? And how? Okay, all right. Is there bio? Wow. Yeah. You did well, Ken. Some crash, but part of It's sugar.
Okay.
Or you can rotate. I don't know if it's long, actually.
And then other times we'll do normal.
Yeah, now I get it. Yeah. Yeah, so right now, I guess I'm still like sort of speculating. It's mostly pseudo, but it should be able to test at least it running like sort of the high rise truck stuff. But so it might require technical training. That would be, fun. ASAP. So, and there's no other type of heat.
So we're going to get started with AIM Stereo Pipeline demo. It'll be when there's 5 minutes left. Yeah. That way you know.
Okay, so do I have to start time or something, or?
Yeah, and I'll leave it when there's 5 left. Yeah.
Okay. So, how many people here have used Inkster Pipeline? Hands? 2, 3, maybe 6? Okay. Hello. Okay, well, hopefully everyone else is at least interested in it. Inkster Pipeline is a free open source toolkit we maintained at NASA Ames, and the main purpose of it is to help digital terrain models from stereo images, and we support most of the input images that ISIS supports, as well as worldview, spot, aster, a few other data types. Through a quick example here from LRNAC data. So it's all just ASP is primarily a command line tool, so I'll show the GUI as well, but mostly we're working from the command line. So in this directory, we've got some data. So we cropped out part of a full LRMAC image to make things go a little faster. So we named the file left and right.tiff, and we have associated RPC sensor models we created called left and right.xml. So the first thing I'll show is our GUI tool. It's primarily a visualization tool, so let's look at the images. So you can just run it, and then it pops up all the images that you input, and you can zoom in, you can pan around, you can choose to tile the images in different ways, like you can put them on top of each other. The alignment's not perfect here, so they don't line up as well, but that's still, if they are georeferenced images, you can overlay them as georeferenced images. So it's a handy tool. It's lightweight. You can look at 32-bit images or floating point images. Another thing you can do is you can query images. So if I click on them, you can see down here at the bottom is displaying the pixel location I clicked on and what the value of that pixel is. There's a few other useful tools. But you can also use it to help run our stereo tool. So that's what we do next. Now, in order to run stereo, you need to pass in a few more arguments to it. So you also need to pass in the camera model files associated with your images. And you also need to pass in an output directory. So let's just call this test. It's output prefix. And then also we need to have the session type. So I mentioned these are RPC models. So I'm just going to paste this in here. So it's a RPC model. And that should be good. So I'm running again. So now I need to, I can pick an area in the GUI that we are going to run the demo on. So we can just try this little area up here. So hold down the control key. I can just select a region. It doesn't have to be perfect. So I'll just try to get roughly the same region in both images here. Okay, just enough. And now I'm just going to run on stereo, and you can see back here it's zipping through all the processing. And this is a small area, so it shouldn't take very long to run. And this is going to run with all the default arguments except for the camera model that I put in. It's done. So let's look at what we got. So it created a directory here in the location we told it to. And you can see that there's so the final output that stereo creates is a point cloud file. But point cloud files are not as easy to visualize. To convert it into a gridded digital terrain model using our point to demo tool. So I'm just call point to demo on that, and again the defaults work fine from this one. Then I can open up that file which is created. And they're going. Okay, that's what we got for a digital terrain model. It can be tough to visualize like this, so you need the option of viewing a full shaded version. You can do that straight from the GUI. So this is the model we got. So let's see. So there's a lot of options you have with stereo pipeline. So maybe you're hoping to get a better quality. If you run with the defaults, usually you get something decent, but there are a lot of options, and you can try again and try to get something better. So let's try rerunning things and see if we can get a better model. So to make sure that we run on the exact same region, I'm going to go back here to the output and get the exact command that we ran. So you can see it told us it's running this command. So I'm going to take that same command. paste it back in. And let's add a few more options here and see if that helps. So we added a new stereo algorithm recently, a couple new ones that are described a little bit on the poster we have outside. So this is a new semi-global stereo algorithm, which in some cases has a lot better performance from one other option. And let's make sure that we write it out to a different location so we don't overwrite our old results. Okay, this one might take a little longer. It's a more complicated algorithm, but hopefully we get better results. The main thing to emphasize here is that there are a lot of options with AIM stereo pipeline. So if at first you don't succeed, well, maybe the right parameter will fix it for you. So that finished up pretty quick. So let's run that. And then we're actually going to go and compare those two output files we got. Okay, so that's a little bit better. Let's turn the hill show you. So the original one we did is on the left. This is the one with our default block matching algorithm. And this is what we got from the new MGM algorithm. So there's still some regions where it didn't get everything, but generally, you know, the artifacts are much less. There's a lot more detail. And you can also compare those with the georeference overlay I mentioned before. So you can put them right on top of each other and just click through to see what's there. Yeah, if you look in this view, you can see at the bottom, it shows you the locations of the images you clicked on, and you can compare the exact values of different locations. So that's just a super quick overview of you know, how you can run stereo using our tool. So some other features that are useful is you can look at the raw disparity values using another one of our tools. So let's just check that out. So this d.tip file is an intermediate disparity file that ASP created, and we're just going to show how you can do that and other steps using the GUI. Okay, so here these are the raw disparity values in both horizontal and vertical directions. These are scaled based on you know, the maximum and minimum values. So that's why the vertical side looks so noisy, is because there's actually a very small range of vertical values. So the images have been aligned, so they kind of look all over the place. But you can clearly see on the horizontal disparity, you know, the underlying terrain, how it impacts that. Another nifty thing you can do with the GUI tool is you can look at the interest points that were used to align the image. That's a little trickier because you have to make sure that you use the images that it used to get the interest points. So I'm just going to look in the directory we just ran for a .match file in this case. So I see there's a cropped .match file. So that means it ran detected interest points between files with those names. So I can just run stereo GUI again, pointing at those files. If I want it to find it automatically, I also need to tell it where I put all the data. So let's do that. Otherwise, I have to manually specify. Okay. So these are the images it used to find the interest points. So I can go to IP matches, view IP matches, and there they all are. So you can see all these interest points. So I'm going to press a key that blocks the two views. I zoom in on that's the wrong key. So now when I zoom in on one, it'll zoom in on the same area in the other image. So you can see, you know, get a good idea how the interest points compare between images. You can even do manual interest point editing if you want. I'll include this one here. Right click. The corresponding interest point is gone. And if I want to add another one, let's just say throw in here. And that point. Let that might drag with the mouse. Okay, so add it over here.
I
ask two questions?
Sure.
Are the images aligned by pixel or are they geospatially aligned?
So there's different alignment options. So these ones are just by pixel, because these are not, these intermediate crop images are not georeferenced. But the first step that Stereo did was try to align them. So they should be at least similar in alignment, but they're not exact. So if you want it to be exact, and you don't know that they're the exact same size, reference images, and if they're not georeferenced, it'll tell you that it can't do that.
And then your match file, can you more that real quick?
Excuse me?
Can you more or less the match file?
Oh, yeah, sure. Oh, actually, no, the match file is a binary file,
Oh, okay.
so we can't do that.
I was thinking it was a control point. Okay.
No, it's a custom ASP file. So if you need to do some sort of manual editing, you'll need to set up an editor or an exporter to turn it to text. Let's see. Okay, so that's mostly it for the GUI and points. So just to quickly go over some other aspects of ASP that might be useful. So ASP does more than just stereo. It has a number of other tools that can be very helpful. One of them is PC Align. This is a tool for aligning. You can align DEMs. You can align DEMs to like MOLA, LOLA. You can align to CSV files. So it's very flexible. It'll do the alignment. It'll tell you how far off they are. What kind of rotations or shifts are needed to do that. So that's a very useful tool. You can also make mosaics out of DEMs and images. There's a DEM mosaic tool for that. There's a bundle adjust tool, which is similar to the ISIS bundle adjust tool, but also work for other ASP supported images that ISIS doesn't support, such as Worldview. We also have a map project tool, which is similar to Cam2Map. It can run in parallel, so you can run things a lot faster if you have a large machine. We also have Camera Solve. This is a relatively new tool that can solve for the positions of a set of images where you don't have all the position data that you want. So for example, if you flew a low-cost drone or you took some pictures with your cell phone, you could then try to make a full georegistered DEM out of those. So that tool can create a solve the relative positions of the cameras. And if you can provide one of several sources of information to help it get into world coordinates, like maybe you have a few ground control points, or you at least have a good estimate of where the cameras were located, it can use that information to put everything into a global coordinate range. Let's see. ASP also is, the stereo itself is designed to run well on large machines or supercomputers, clusters of machines. There's a version of stereo called parallel stereo that will split up the work like that, so you can get your tasks done a lot faster. But yeah, that's real quick for AIM-Stereo pipeline. So it's free. You can just download it. We generate binary installations for Linux and for OS X. So you can just download it, unzip it, and you're ready to go. You don't have to compile anything. We have a large documentation file, which hopefully has the answers to your questions. And again, it's free, so check it out. Oleg and I are always monitoring for questions, so if you need technical support, let us know. I'll try to help you out. That's all I had, so any questions?
Is there a procedure for doing global mosaics, analysis, or versus global DEM?
So the tool should work in general on arbitrary sized DEMs. I'm going to guess that you might run into some issues if you're trying to do a very large one, but probably it's something that we could work out. I don't know if anyone's actually trying to do global scale work ASP before. So, all right.
So I think I'm going to get up there next, and Trent's going to keep me honest on the time.
So this is a demo by Jay Laura and Moses Camazo.
Just by day.
Just by Jay.
You're not gonna juggle?
Run laps while he does that. Python tools, auto CNET, and camera. Didn't you have a third one in there?
There's some IO.
A little bit of IO, so a little smattering of everything Python.
Working, sweet. Let me just see if I can get the resolution to be a little less cruddy.
So if you guys noticed, I didn't have a camera model poster. I'm going to make the excuse that Jay was going to do a demo of it, so I didn't need it.
All right, so I guess this is, the entirety of this is a plug to go to that GitHub URL and check out some of the work that we're doing and open up issues, pull requests, tell us what's working, what's not working. We love to hear from people about how our stuff can potentially integrate with your stuff so that we can start to be working together. We're going to spend a bunch of time tomorrow morning talking about this whole TSDI concept. So this is kind of the USGS Python tech component of that. So I figured I would do this live because it's more fun if it eats it. So yeah, we'll see how that's going. This is a really sweet Jupyter notebook. Like I said before, we do a lot of work in the Jupyter notebooks. All right, sweet. So first up is Trent's poster in presentation form. We're working on the community sensor model. It's originally a terrestrial sensor model made for the military so that they could accurately do all of their military type stuff. The idea is there's one single standard interface that we're writing to. It's not a mix and match camera model. Kind of does whatever you'd like it to do. It's a pretty strict standard. The models are here I'm being polite and saying simple. They're really dumb models. They don't do much, which is awesome because from a development perspective, you can focus on limiting your interface to your sensor model and then making sure that it's not spiraling out of control and out of scope. We have 4 different modules in the community sensor model. If you go to USGS astrogeology and you use the GitHub nice little search thing, CSM hyphen, you can see what's hiding down there. Let me actually back up one here. So the idea basically here is SciCSM is a Python wrapper around the community sensor model. Community sensor model is written in C++. I like to work in Jupyter notebooks, so why not just wrap it? So it's wrapped in Python for Python access, which is really sweet. The set is a sensor exploitation tool. It's basically us using the sensor model. And then way down here off the screen where the resolution fails is one called camera model, I believe, or CSM camera. And that's our actual camera that we have written in C++ and again wrapped in Python. So, how exactly can these cameras get used? We basically build this ISD. The military loves acronyms, I think, more than planetary scientists, and so this is covered in acronyms. ISD is image support data, so we go ahead and create some image support data, instantiate a sensor. That's a 2-step process because the CSM is a little weird there, and then we exploit the sensor or use it for doing something. So SciCSM, like I said, is a Python wrapper. Right now we cover about 40% of the CSM standard. There's some components we haven't needed to touch yet. There's a bundle adjustment API that they've written, which is awesome. There's a raster data API or spec that they have designed. We haven't needed to touch those. As we need to touch more components, we go ahead and get those set up. One nice thing is all of our testing of the underlying C++ is done in PyTest, which is a really nice framework. So we're testing at the Python level, which makes things way easier. The other modules consume the CSM, so there's literally nothing to demo. We're using this API. All right, so then creating image support data. In the future, I think Moses answered a question about REST and Spice. We're hoping to be able to create one of these image support data things out of a RESTful service. So plugging Andrew's project, SpicyPy, is a great way to do that with Flask. So we're hoping to check something like that out in the future. The ISD is JSON, because JSON is, I would argue, super human readable, lightweight. Works wonderfully on the JavaScript side, so it's a nice non-spec spec to be conforming to. All right, so now comes the really scary part. We're going to do some imports. For the PVL maintainer, there's no recursive find in the PVL library, so this little guy gets used all over the place. It's just recursive key searching. Find it on our GitHub page. So unfortunately, right now we're having to furnish all of these kernels independently. Meta kernels would be the way to go. And so this is like we talked about. This is something that we are working on. This is a pain of going through and being like, what kernels do I need? What order do I need them in? This is not something that any scientist or developer should ever have to do. All right, so the ISD is literally a dictionary. The idea of throwing all this code on screen is not to bore you to death, but basically to say computers should be doing this, not people, and so we are working on automating this. These parameters should all look really familiar. This is what you need to make a camera model. This is some of what you need to make a camera model work. Things like focal length, understanding pixel pitch, bore sight, understanding translations. It's all buried in here. It all gets piped into a JSON file. This is for Mercury MDIS NAC. The freebie that we got with it is a word for MDIS NAC too, which is absolutely awesome. There's a distortion model defined in the IK kernel, I believe. Somebody correct me if I'm wrong. So we need to go ahead and apply that. It's a temperature-dependent focal length. One of the distortions is temperature-dependent focal length. So there's our function. We need to go to, we're using ISIS cubes because we've got them in-house and they're easy. This information to support these ISDs could come from anywhere. You could get a letter in the mail that tells you what to do. You can make up your own numbers. So there's lots of options for where it comes from. So again, PDL module, which is absolutely awesome. Some other information that we need to make the camera model work. It's really nice to know kind of what you're looking at and what you are. Semi-major, semi-minor axes of the body, and then we go ahead and we add the temperature-dependent distortion. Run it. We need to work with time. It's a framing camera. Chris, enlighten me. Just take the middle and you're good to go. Do that. Nothing magic here. Just a computer should be doing it in the future. Position, obviously, is super important. Again, we're sitting on top of Spice. Here it goes. Andrew, again, thank you. This is SpicyPy in action. Got the sensor origin with respect to Mercury. Orientation, the CSM works in Omega Phi Kappa, so if you're not working in Omega Phi Kappa, if you're working in the off-pitch roll or something else, we need to convert to Omega Phi Kappa. Spice guys, thank you. We're able to get Omega Phi Kappa out without a problem. So I spent about 2 days of Trent's money being totally confused by the fact that Spice does not send Omega Phi Kappa. I don't know why it was like this mantra. It must come out Omega Phi Kappa. It doesn't out of Spice, so just be careful if you're ever there. Read the documentation. Sun position and spacecraft velocity. The velocity not so important here. The sun position definitely important because we want to have a sensor exploitation tool where we can do stuff that Tammy showed before, like incidence and emission angle. We need to know where the sun is. We need to know where the body is. We need to know where the spacecraft is. So more Spice. So the CSM, where I said it's kind of dumb, it has no concept of a shape model inside of the camera. And so the camera is intersecting the look vector with a 2-axis ellipsoid that Trent has now allowed us to vary in the newest CSM spec. And so you're saying, well, this isn't very useful then because I'm stuck with a sphere or a 2-axis ellipsoid. The idea is that intersection with the DEM and use of the DEM exists in some other module in some sensor exploitation tool. And so the CSM does a nice job of forcing the developer to modularize their code. So we go ahead and plug in a min-max elevation. These are our initial guesses. These are random numbers right now because we haven't built a shape library yet. I think, Trent, we're doing that in October, maybe? All right, sweet. We're doing that in October. And we're done. So now I want to go ahead and write that out. This is just a little block for how to use JSON encode and NumPy array. We're good to go. And oh my God, it's a big mess of JSON. So this is screaming out to be really easy to use and some web-based microservice, and not for a scientist to have to go through all of that trouble. Basically, let the backend load the meta kernel, go ahead and dump out this JSON file, and now the CSM is actually able to do what it wants. What's really nice though is none of this is internal to the camera model. So all the camera model says is I want information with these parameters. And so again, the CSM is forcing us to break apart this code into nice, cleanly separated modules with well-defined interfaces. So this is my plug for like, as a Flask app, it would be really awesome to just send out a request and say, hey, here's a JSON blob with my necessary metadata. Like, this is what I am, this is what I'm looking at, stuff that you get out of your PDS header and get back in ISD. So then we go ahead and we instantiate the sensor model. So the sensor model is written in C++, so it's faster. We go ahead and load the ISD, we create a model. The CSM uses this concept of models and cameras. It's basically just namespacing, and then we're off to the races. All right, so all these includes for all you Python developers should look pretty regular. Maybe it'll work. Sweet, all right, cool. So here, we loaded the ISD, we created our camera, we loaded the ISD, and we're just querying for different parameters. So we're hitting that C++ API under the hood. We can see that it is an ISD object. So create the model. Again, this is this namespacing stuff that's going on. All right, so here's the magic. We're going to go from the image to the ground at pixel 512, 512, which should be the center. And then we're going to go from the ground back to the image. And we can see here it worked once, so hopefully it works a second time. All right, sweet. And it worked within our rounding errors, so we are happy with that for now. That's running temperature-dependent focal length, the distortion model out of the IK kernel. So we're utilizing all of the stuff, if you will, that we need to use. So Python's really slow. It's super slow. It should never be used for camera model. And what we'll see here is out of 10,000 loops, we're looking at about 97 microseconds to do 1,000 camera model to, or image to ground runs. So it's not actually slow, which is totally awesome. Incidence angle. So incidence angle is us exploiting a sensor model. So it's not inside the sensor model, but we know that we need to use image to ground. We need to know some illumination info, and then we need to go ahead and compute some angles. And so we can go ahead and do those at the center of our image. So this is an example of basically saying, I'm going to utilize my camera to do something, whatever that is. Here's another kind of proof is in the pudding one. So this is a cube that we want to go ahead and run through. We need to project it. I don't know if I ran the last cell. I don't want to switch to the canned version on you guys. Let's see. All right, sweet. So unprojected, we have the array in memory. It's NumPy array. We're going to go ahead and project it. And in projecting it, when I say projected, what we basically just did was took all the pixels and pushed them into down onto the body and body fixed. No DEM involved. That's really nice, but I like lat-long, so I'm going to go to PyProj because Proj4 and PyProj are awesome, so why not use those? I don't need to write my own projection engine. I don't have time. Kansas data frame basically saying pixel, this would be 0, 0, they're not indexed. Here's lat, here's lon, here's the DN value. This is slow because matplotlib is slow. So this is going to take about 30 seconds. Maybe I'll skip it and then come back up to it. But basically what's happening here is we're taking all of these individual DM values that have been converted into lat/lon and then interpolating them into a raster. So that's all this code is doing. This is regular, boring, if you will, boilerplate Python. I'll come back up in a minute. Just to show you that it finished. This is what it looks like then once we get it pushed down onto the surface. It just finished. It didn't finish. All right. It's messing with me. And so we can see now that we've been able to exploit this sensor to go ahead and get the image down onto the surface. So right now, this is us working with the sensor models. We have one for MDIS, NAT, and WAC. There's a huge overhead for the user having to go ahead and come up with all that ISD stuff. So I'm not here saying, hey, because you shouldn't be using this yet. It isn't ready for use. Because we need to work on some of the ISD stuff up front so that you don't need to worry at all about what's going on with Spice. Basically, what we want to show you, though, is we're working in a standard. We're working on wrapping the C++ in Python so that it's usable both by your C++ developers and your Python and potential Python science users. And we want to show you that, yes, it does, in fact, work. This is live. Am I doing it right on time? I don't even know. All right, sweet. So that was 10. Awesome. Sparse image matching. So this is what I talked about a little bit yesterday. So today I'm going to slurp some images, apply some CUDA magic, throw out some outliers. I've got a slide in here from my Bland. I'm going to run an ISIS3 bundle adjustment, and then we're good to go. Oh, that's killing me. All right, sweet. So basically, I talked a little bit about it yesterday. We're doing this dynamic dependency injection on a live object, which is a ton of fun. We basically say, hey, if you have a GPU, we're going to use it for you. And if you don't, if you have 2 GPUs, you tell us which one you like the best. And we'll go ahead and we'll try and use that one. Here we can see, I think I have 9 apollometric images pulled in. We can see this adjacency overlap graph with the labeling. This is sitting on top of Network X, Pandas, NumPy, SciPy. We basically glued a bunch of great libraries together to solve our problem. I should run it. Hopefully it works. All right, I'm just going to go with it. We'll see what happens. So extracting the interest points, like I talked about yesterday, CUDA, 32-bit. Nice typo there. Works on full images, downsampled images, tiles. That's just what yesterday I said we can chunk through Trent's 40 gigabyte mosaic. It's because we can tile it out. We can understand how much we want to overlap in there, because when you're doing the extractions, it's pyramided, different Gaussians. So we want to make sure that we deal with different edge effects. Here we can see key points. Like I said, it is a Pandas data frame. And so any of the analytics that you would apply to a Pandas data frame, you can apply here. So you can interrogate your data however you want. You can query it with SQL-like syntax. Let's see if this is back working yet or not. Keep going. Oh, did it come back? Sweet, it is back working. All right, so that just ran live. We just did a CUDA extraction on there, and we got back our images. We're going to match now, also CUDA. We'll run Lowe's ratio test inline in the CUDA. We'll skip the symmetry checking, the whole, does image A match image B, does image B match image A? We're safe to do that. Ratio is 0.9, like I said. I talked a little bit about yesterday. Again, a Pandas data frame comes back out. This Pandas data frame is indexed back into the key point Pandas data frame. So the lineage of the key points to the matches and on is tracked through all of this so that we can go back through and understand what's going on. So like where are the matches, which key points are the matches coming from, which level and difference of Gaussians were those brought in, what's their response, yada, yada, yada. It's all tracked in here. And so we plot this. So this is the result of Lowe's ratio test, and clearly we're ready to go. We can bundle adjust off to the races. The pickup sticks correspondences look absolutely great. All right, Mike, this one's for you. We had a wager to have 1980s cartoon characters in our slides, so we've got it here. The reason it's in here, though, for real is, like I said yesterday, we want to talk about different distributions, right? And so Here I'm basically saying compute the fundamental matrix. This is something, if the Ames guys are still here, I want to talk to you about how you're using homographies, because they don't work for me when there's topography. So it's something that I'm curious to know what you guys are doing. So fundamental matrix here, and we go ahead and compute the box plot, and when it all fits on the screen, maybe I can shrink it even more. Yeah, we can see we've got nice reprojective errors. I didn't code any of this. Pandas does this for me. I just get to use it. So this isn't some like magical thing going on. This is me using Wes McKinney and his team's good work. So then we've got our fundamental matrix, and we can see here these are Apollo 15 metric. Hey, this doesn't look like pickup sticks anymore. Awesome. We're getting closer to what we actually want to see. We're in good overlap. If we took these two images and flopped them, we would see that they overlap with each other in the mountains. I think these are the same images that Ken used in his demo, even this popular place. Let me see, have I been running stuff? I hope I've been running stuff. Nope, all right, I haven't been running stuff. All right, I'm gonna go can for a little bit. So then what we basically say is, hey, that's way too many points. Tammy would tell you that you don't want too many points between all of your images for when you go to bundle, especially if you have a lot of images, because then the bundle gets relatively unhappy because there are too many points. And so we apply this spatial suppression algorithm. We basically say, what did I say here? Find me the 50 best and keep those based on reprojective error. This is one of the reasons that if this was a Python conference, I would be telling you guys about how awesome Python is, because I'm passing in a function here that says, hey, I want to apply this function and return a Boolean mask and do a whole bunch of fancy stuff. So functions is first-class objects. All right, so then I'm going to go ahead and I'm going to generate an ISIS control network. So this is an ISIS compatible control network. We go ahead and create ISIS compliant serial numbers, so you don't have to worry about doing any of that stuff. This control network just works in ISIS, which was super important to us. All right, so now we're going to bundle using ISIS. I'm not going to open up any ISIS applications. The parameterization follows. We're just mirroring the ISIS API right now, so we're going to make it more Pythonic, right? Why does everyone wrap GDAL 600 times? Because they want it to be more Pythonic, right? So we'll set up the arguments. That's the not Pythonic part for you. If that doesn't look like C++ written in Python, you don't know what does. Perform the bundle. So here, Koleski for the bundle, we return 1,592 control points. I didn't do some of the additional outlier detection and that kind of stuff because it's a demo. Whoops. All right, we're going to analyze the results. We get the results back as a pandas data frame. That is a function that if it fits on screen, just converts stuff into a pandas data frame. All right, and here are, this should look like results.csv, I think, out of the bundle, but as a pandas data frame. You will see here as I scroll to the right that I did a really bad job with my matcher because I wasn't worried about it. And my residuals are absolutely just gigantic. But the point is not, in this case, to make a nice mosaic for you. It's to show you that we just ran the bundle. We're getting the results back as a pandas data frame, and now we can do additional analysis. What does that additional analysis look like? You guys are tired of seeing box plots, but here's one box plot. Essentially, we got it back as a pandas data frame, so why not use pandas? So box plot of the residuals after an SQL-like query has been run to say find me only those where rejected is not false. All right, so now I want rejected is not false and magnitude is less than 50 because I'm going to throw those out anyway. And then say, you know what would be really sweet? I would love to see a quiver plot that shows me the residuals. I want to see the XY positions of the residuals with their magnitudes, their residual magnitudes in line sample. And so I can go ahead and visualize that. This, again, looks like pickup sticks. If we're doing this for real, we spend a little bit more time. We actually parameterize the bundle well, and we get these that are much more meaningful. And we can say, hey, there is totally this weird spatial clustering that's happening over here with our residuals. Let's go back to our original data and check out what's going on. So the idea here is to be able to interrogate our data. All right, hopefully I got like 10 minutes left, 5 minutes left. All right, sweet, 5 more. Plyo. I'm tired of writing the same IO code over and over and over and over again, so we made Plyo. Here's all our badges. It's got a whole bunch of different modules. Some of the fun ones are, this is for Robin Ferguson, go back and forth between Elsevier, Marzier, Ephemeris. We can read QB Spectral Profiler and test data. If for some ungodly reason you have Hugh-Keefer's KRC thermal model data and you want it as a pandas data frame, this is where you go to get it. So spectral profiler, here's ancillary data. Whoa, real pretty. It's a pandas data frame. Here's the actual spectra that come out of it. So the raw, the ref1, the ref2, and then their mysterious QA. It's not really mysterious, it's their masking stuff because it gets super noisy between the two sensors, but it's all in there. Again, it's a pandas data frame, so you can do whatever you need to do. Pretty picture. I didn't write any of the plotting stuff, Wes McKinney did. Same thing for test data. So somebody was like, hey, I think it was Michael. Hey, can I get at the test data? Here's the live example of us pulling the test data out. We're pulling just out of one tab file. So they've got, it's basically primary key. They've essentially done a normalized database to file. And so you want to pull, say, from different orbits and pull all those directors in one place and then use pandas to just aggregate them into one super wide data frame and watch out for when the primary keys don't match up. That's always fun. All right, and then last but not least, I threw this in for the mappers. Are there any mappers left, or have they all run for the hills? All right, sweet. Latitude-dependent scale bars. I built this for Trent. I didn't know why I was building this. Now I understand why. It's out on GitHub. It outputs to SVG because, as you'll see here in the notebook, the SVG rendering puts some of the numerics right on top of the scale bar. It doesn't do that on a desktop. I don't know what's going on with Jupyter. And there it is, super duper pretty. We basically took a well-known text string, we piped that in with a little bit of additional information, and we get an SGV out. And all we're doing here is reading the SVG, I think I keep switching those back into the notebook. Here's polar stereographic off of an image. So we're going, we're opening the image in GDAL, and we're saying, hey, GDAL, give me your projection string so I know where to draw all of these lines. So we go ahead and draw these lines. We can do mirrored, single, yada, yada. But if you need to do a scale bar and you need your scale bar to be latitude dependent, we've got a Python library for that. And finally, this is, again, where all of this stuff is living. So please open pull requests. Be like, hey, I've got an issue. This doesn't work. That doesn't work. I just got an email about a project that hasn't gotten touched in 2 years. Something wasn't working. We're getting it fixed for the person. So just because it hasn't been touched in a while, it just means that we're not funded to work on that right now, but fix them. So thank you. That's all I got.
I do have one. What do you see the use case for Plio? Just as it's just a generic way to put a bunch of different discrete I/O.
Yeah, so it's a generic namespace essentially for putting a whole bunch of discrete I/O readers in. And so there's a lot of these data sets that I'm like, I really want this as a pandas data frame so I can do something with it. And I end up, for Robin's project, I write a KRC reader so that I could get at it as a pandas data frame. I have one for spectral profiler. So I had these kind of scattered all over my workstation. And I was like, you know what, I'm just going to pack them all into one place, stick them in a namespace, and I am good to go.
The concept of Planet Pi, or Planetary Pi.
Yeah, I mean, if I could hand that off to Planet Pi or Planetary Pi or any P-Pi, that would be, absolutely awesome because there's tons and tons of different readers out there, I think. And if we can standardize what they look like, so heterogeneous data in, homogeneous representation once we're inside, that would be absolutely ideal. I would advocate for pandas, but if someone's got pandas 2.0 or something else, that's absolutely fine too. We know that image data, quote unquote, doesn't necessarily lend itself to being pandasized, and so that's something that needs to get thought about. But yeah, I mean, that is right for the picking, I think, because I'd love to see us get past I/O and into more analytics. We spend so much time on I/O. It's way more fun to do analytics.
We'll set up the station for Emily Law. She's going to be talking about the trifecta, Mars, Moon, and Vesta. I guess there might be more because it says etc.
Go ahead and do. Everybody, good afternoon. Okay. Good afternoon. Thank you for having me here, and I'm just going to use my name is Emily Law from Jeff Bush Laboratory. I am the lead of the development team that built all these tools called the track portals. And I'm going to use this opportunity to quickly give you an introduction. I'm hoping that we can go through this slide really quickly and allow me to have some time for doing live demo if possible. So quickly, an overview is that these portals are basically a set of web interactive portals provide you access of data products as well as interactive tools, for explorations, maybe for mission planning, scientific research, and also public outreach. So you can use these tools, without having to install anything. You just go to the Chrome browser, and then you can type in the URL and you can start exploring the different bodies that we have ready, currently ready, available, publicly available. So basically, what we want, is to provide the visualizations and also an analysis for the data sets that we collected from different spacecrafts and the different instruments. So in addition, for providing the user interface, we also provide data services allow a number of different external interfaces to be able to use our data. For example, the icon solar system and some planetary planetariums are actually using our data to show off, that capability. And it's actually, we are, the tools that we built is applicable to a wide range of planetary bodies. So the background is that we actually started back in 2009 from the Constellation program. Initially, we released something called the Lunar Mapping and Modeling Portal. I don't know if anybody have experienced it, used it before. So, Trent has, and now we have, evolved, and now we have expanded it to also allow explorations on the moon, not just the moon, but also Mars and Vesta. So we have released the Mars track back in 2015 as well as the Vesta track, and earlier this year, track which actually replaced the LLMP, which is having the a better, much better interface for that for usability as well. So from LLMP to Moon track again is really a major release for us to upgrade both the front end and the back end, and also make sure that the user interface is compatible with the other tracks portal like the Mars track and the Vesta track. And also, what we really improved is the 3D globe view and the 3D navigations using the game control and allow you to be able to fly over the surface of the moon. So basically, all the track portal has similar capability, which is including a set of analytic tools. For example, lighting, slope hazard, which is like rock and crater detection, also sun angle, and also profiling of the terrain as well. You can search and also download the data product, visualization with overlays, and what we call bookmark is you will be able to collect a set of products and then share it with your colleagues. You can also do 3D printing and also 3D navigation. For the Moon track, we have a large number of data sets from different past and also current missions. For example, LRO, Apollo, Clementine, so far and so on, from different instruments. So we have different type of data products for example, mosaic imageries, DEMs, so forth and so on. So again, portals are, geared towards all the different users in terms, specifically for mission planners, also the scientists, as well as the public outreach educators as well. So this is a quick movie. So once you get to the portal, moontrack.jpl.nasa.gov, you can zoom and pan. And then right now we zoom into the Tycho crater. And you can use the tools. One of the tools is called distance tool. So you will be able to draw a line or a polygon or freehand, and you draw it across the crater to try to figure out the distance. And the distance is 83.76 kilometers. And then you can also, again, draw another line and be able to give you the profile. So again, you draw a line across the crater, give you the distance, and you submit it, and there's a plot and the profile into a CSV file as well. So in addition, once you find an area of interest, you can draw a bounding box, and then you would be able to create a 3D print from it. Basically, it will allow you to generate either STL or OBJ file. And with OBJ file, you'll be able to add texture on top of it, and then you feed the file into the 3D printer, and you'll be able to get the model like that. So here is another movie, I believe. Oops. This is basically to show you, our flyover capability. Using the game control key, which is the WASD key, you'll be able to do this kind of flyover the surface of the moon. In addition, eventually you'll be able to allow you to plug in a joystick, and you'll be able to do this things easier if you're not a gamer using those game control key. So this is just a taste. So for lighting analysis, again, if you find an area of interest that you want to do lighting analysis, we allow you to be able to do that. So here is an output of the lighting analysis. And then it would also output a plot like this, which is telling you the watts per square meter. And it will be useful for your rover planning if you have a solar panel, for example. Another tool example is the slope tool. Once you use this tool for a specific area, you'll be able to get a contour map. And there are also other maps already generated or produced by the moontrack as well. So there's other analysis tools coming. For example, I mentioned about crater and rock detections. Here is just to give you a preview of what the result that you might get from those. This is a rock and crater detection output. You can tell that it's using machine learning capability algorithm to detect those rocks and craters and give you this map as well as a distribution plot. Working on subsurface potential analysis. This is the result of it. We partnered with a survey PI, Barrel. Rhythm is allow you to provide a result like this kind of map, as well as a plot like this to tell you the ratio of the surface ion flux to the solar wind ions, for example. And another tools that we are working on that we would like to incorporate is called Pack Tool. It allows user to identify a starting point and ending point, basically using the slope to basically draw the optimal path. And then you will be able to go traverse the path. While you're traversing, you will be able to look around and look at different view from there. In addition, you will be able to add different layers to it as well. Because for the moon track, we have over 700 layers of different type of products. So, for example, we added I believe this is the logo mosaic. And here is another type of products that lay over on top of it. Move on. This is just show you some different products that we have from the node codes. We have the mag mosaic. We also have the minor average temperature and the maximum temperature. And here is the CF mosaic, 128 degrees. So let's move on to Mars track. In addition to the moon, we have Mars track, JPL Banana Setup. Again, it's the same idea. We have all the different tools and different products from different missions and different instruments. So quickly go through some of the examples that we have. This is we have the Mars exploration zones here. NASA is working on focusing on the human exploration landing site collections, and this is some of the zones that are given to us. I believe actually Trent has given us this layer. We also work with Nancy Cara Natorola. She and her student have provided us, the exploration zone in much more detail. This is an example of the 100-kilometer diameter zones that we are working on. And here is a rupee. There you go, sorry. This is, again, just to show, the 3D capability allowing you to fly over. And while you're flying over, you can put on different layers. Again, this is something that you can do on your laptop. And here is some other different app, wells, and on top of it, we layer with the CTX mosaic. The file is the CTX mosaic, and we overlay it with the crystal data product that we have heard earlier during this meeting. This is the polyhydrate sulfides. That's the chloride deposits on top of it, and here is the iron mineral. So we also have that, if you put pins on where all the hydrous minerals, have been detected on the global mosaic here. We also have geologic maps that we can lay on top of the surface, as well as the recurring lineates and new craters and active gullies, footprints on this mosaic. Here's another movie, I believe. So this is just to show you that, you dive into this crater, and the high resolution data sets that, you'll be able to see, and you'll be able to do it on your own on the laptop to go through the area of interest. Delicious. In additional moon track and Mars track, and we also have Vesta track that's currently publicly available. The same idea, we have tools and also the data set allowing you to do 2D and 3D visualization as well as exploration. So those are the ones that we currently have that you can try. Just go to your Chrome browser and, call up the URL, either moonstrack.gmail.com or marstrack.sg, and you'll be able to do, what I showed you earlier. I just want to give you a peek, preview of what we are working on right now. Headquarters asked us to work on mobile track, so here is an example. Well, here. This is just a quick preview of what you are able to see if you play with mobile tracks when it's available. The 3D models here, and you'll be able to have different type of data sets that we currently have. For example, we have this PNIR mosaic. And we can look at the albedo. Deleted ideas. So another product that we are working on is the comic C3, which you all know that Rosetta belongs to this comic. So it actually, is the irregular shape very different from Mars or the Moon. And what you can see is the both sides from actually the Rosetta, and the instruments where it's looking at while rotating the body. And that's oxygen. So also, I talk about not just providing the products and also the portals, but also our APIs allow different interface to be able to utilize our data. So, so we'll be able to serve a different kind of clients, including touch table, virtual reality goggles, and also the different handheld devices as well. So using this, I hope that I use this opportunity to introduce products, and when you play with it, there's a contact capability allowing you to be able to send us feedback and any improvement that you would like to see, and I'm hoping that this will be useful for you. So how are we doing in terms of time trend?
Still have about 10 minutes.
Okay. So by the end of this, I'm hoping that maybe we can quickly just be able to do some live demo. This is the moon track. See what we can do here. We have shown you that there's many different type of layers. So what you can do here is you can find the layer. For example, in here, you can go find type equator, for example. Then you will see a number of, products that are related to the typo equator, and you can pick any of them. Let's just pick one of them, and it will be you'll find that and give you some information, and you can add that to the map. And you can find there. Well, once you add the data, let's go ahead and add additional data to it as well. So let's pick another layer, perhaps there. We can also add that in the portal right there. Now you see that, you see only one layer. But if you use this tools here, you will see there's actually two layers. And we have a transparency bar. So using the transparency bar, you will be able to correlate the two data layer that you add to the portal. And there's a number of functions for each layer. For example, you can do toggle the visibility of that, provide you information, fly you into the position which we are already in. You can also toggle the legend. So there's, will give you, click on that, you will see the legend of the layer. We also have, we're detailed metadata, so when you click on it, you'll be able to get the metadata in full detail for each of the layers. And the other way, thing you can do is once you have multiple layers, you will be able to reorder them. For example, so this one now is coming on the top. So when you have 3 or 4 layers, you will be able to reorder it the way you want it. In addition to adding the layer, from finding the layer and then add to it, there is a explorer capability down here. So what it does is similar to the Google Earth, so allow you to see that, in the viewing window here, what are the layers that are available. So you would be able to just go ahead and pick the ones that you can right from here. And then you can add to what you're looking at as well. And now you have now you have the 3rd layer being added to it also. So those are the different capabilities. And also once you have a collection of the layer, you want to share it with your friends or colleagues. So you can just click on this share link here. You can either take a screenshot or you can share the link, basically copy this URL and email it to your friends, and they will be able to see the same collections that you have in the way that you have layered them. So that's the moon track, and the moon track is the same idea. Again, we'll have different tools that's available. Currently, Mars Track has a little bit older interface, and coming this summer, either later this month or early July, we actually going to release a new version that have the similar user interface with the moon track. So I think that's about
Can you open up the layer list again?
it. Which one?
The layer list, maybe on Moon Track if you still have them. You missed my favorite button,
Which is?
download.
Oh, okay. So once you select, sometimes there's a download button that you'll be able to download the later onto. But you're downloading basically the layer, not the PDF product. Although all the layers are built on top of the PDF product. And a lot of this, majority of these products are actually generated by Trend, so thanks to Trend for providing those products to us. Okay, have any questions? You want me to show you anything else?
Sorry. You said illumination again?
I'm sorry,
The
I can't.
illumination? The illumination.
The illumination?
Second on time.
So, whoops. Oh, I closed it. Hold on. I should be able to open it back up. Where is it? So, let me see. I think it's here. This guy here?
Where is it? I think the question was where is it in the interface?
Well, where can you find it? Okay. So when you go to windtrack.jpl.nasa.gov, it was first start off with asking you whether there's a tour. So I would encourage you, if it's the first time, go ahead and, start the tour, else, you can skip it. So what happened is when you first started, there's only basic tools for the general public. So what you will need to do is go to the menu, sign in, and if you put in Moontrack 1, log in, and voila, you will have the additional tools that show up there. So here is the service lighting.
So that the password was moon trek? Trek moon.
Yeah. And so you know, do a rectangular box somewhere, and then we'll give you the parameters, and then enter your email address and submit, and then you'll get the results sent to you when it's done. Yeah.
Is there a reason to log in to have these
Yes.
special things?
Because there's a lot of processing include, involved in there. And we actually using the Amazon cloud
Amazon
computing,
Cloud, okay.
and there's a cost associated with all this processing that we do. Want to really limit it to people that we really need to do their research as well as mission planning. So we don't want anybody to just go in there and start a job and then, it might not necessary for them. And particularly for a lot of general public, this is, in a way, it's outreach tool. They don't need this kind of tool. They wouldn't understand how to use it. So we don't want to have to, make it available to just anybody.
Okay, is that the documentation written that you have to log in to get these special things?
Yeah.
Okay.
Mm-hmm. Yeah.
I was wondering how many active users do you have per day per week? So, can you measure that?
We actually don't keep track of it. We usually look at using Google Analytics, and we look at it from time to time, particularly when we first release it. Initially, for example, Mousetrack, last time we looked at it, there was, just the first month, we have over 2,000 users.
So I was wondering, because it's so highly dynamic tool and very graphical, what is actually offered by the REST API?
What if I can't hear you?
What is offered by the REST API? Because
okay.
It's so dynamic and graphical, so I'm wondering
Right.
what you get.
So the REST API is really to get the data access. So you'll be able to use our API to actually get capability, for example, as long as you know what data you want to get. So it's the data sets that you are accessing. The tiles, for example, what's this tile? You will be able to get tiles that you want, so that if you have your own clients, you'll be able to show those tiles.
Okay, so it's basically the data you use for the displays,
Right.
all your inputs I could get.
Right, correct. And also all our tools, all our analysis tools are web-based as well. API for accessing those tools. So that means you will be able to, as long as you provide clients that use the same API, same web services, you'll be able to get the same results.
Okay.
So it's both tools and data.
Have you yet implemented the high-rise DEMs?
Yes, we have some of the high-rise DEM, and in fact, using the stereo pipeline, we are building our own pipeline to be able to allow us to quickly generate pick stereo pairs that we want, and using the stereo pipeline and come up with a high-rise DEM. Particularly, we are asked by Jim Green, the SMD Science Mission Planetary Science Director, to focus on the human exploration and insight selection. So we would like to populate Mousetrack with all the 40 whatever proposed landing site zones to have as many high-rise DEM as possible. But they're huge. When we go to find high-rise strips for those areas, there's only several, very few of them. We'll be able to either figure out what's the best stereo pair and be able to generate those DMs. So eventually, we're hoping that we'll populate for all the areas.
Okay, thanks.
Yeah, I think it's actually pretty accessible. If you look for Mars Trek NASA API, you can find the REST interface for the WTMS or WMTS or whatever it's called. You should be able to use that in layers.
Right. They are all in under API.nasa.gov.
API.nasa.gov.
Yeah, because we provide all those APIs for the space challenge, for example. People are actually using them for their project.
questions?
Thank
All right,
you.
thank you. Move on to the last topic. This is Scott Aiken's PDS imaging PAL and MapTube tools demo.
Can you hear me? All right, so I'm Scott Akins from the USGS, the Astrogeology Science Center here in Flagstaff. And I'm going to talk a little bit today about some of our web-based image processing tools for map projecting PDS data. We have two tools for that, map projection on the web and Map Planet 2. A lot of times people want data that they can use in tools they know, but they don't necessarily want to learn the tools to create those data products. And so we're trying to simplify that. Underlying behind this is ISIS and GDAL and some of the other tools that you've been hearing about today. But let's say you want to work in ARC or something else and you just want the images map projected and ready to work with. So these two tools provide web-based, simpler interfaces, but give you most of the capabilities you're looking for. So who's using the tools? It's open to sign up for an account. Anybody can. We have researchers, students, educators all over the world. Every year we get a huge chunk of people signing up from the Mount Shasta School District in California. They do a lesson plan where they search for images on Mercury, map project them, pull them into QGIS, and then look for possible landing sites for a future. We've also got a lot of community members. A lot of the people who sign up for accounts want to make image backgrounds for video games. This right here is an example of somebody who, they actually give a great overview of using the tools. They got an image from the Astropedia of the moon, map projected it, and then did some processing and used it with a laser cutter to build a notepad with its texture. So some of the current capabilities for the map projection on the web, it works with the EDR data in the PDS, lets you specify map projections, boundary clippings, set your file format for whatever you're working with, including GIS headers. And then the pipelines are using known pipelines within the USGS to try and improve the image quality for the different instruments you're working with. So you don't necessarily need to learn all the details of each instrument. Here's the instruments currently supported. This is based on whether there's an ISIS 3 camera model and a couple other pieces we need to make sure we can provide the full functionality on the back-end side for the processing we do. Most of the talk goes through how to use Map Planet 2. So real quick, we'll just break out of this and do a demo using PAL. So for projection on the web, you start out in Pilot, which is our tool for searching for EDR data in the PDS. Oh, is it on? Okay. There we go. So pilot, HTTPS pilot, WR.USGS.gov. This is the search interface we have for the PDS images we processed. And this all goes into a database so that we can keep track of keywords and which instruments are eligible. So first thing you do is pick the target you're going to look at. And next you can select instruments you want to work with. For this, we'll just use Mach-NA. Next step is to move on to the map and kind of select the clipping area you want to look in. And to do that, use these controls on the left. This one's the bounding box control. It's not as intuitive as everybody would like. To do it, you click to set each point of your bounding box, and then double click to close it off. And this is going back and looking and seeing what images are in this area. So for each image match you find, you get a little bit of information. There's info on the image in terms of the instrument keywords. You can see where it falls on the planet. You can download the raw image here, which is the PDS image. But if you go up here and select download or process, this can work with a set of files or individual files. And your download options. Let's close this real quick. Oh, you can actually highlight. There we go. CSV or a bash script that'll download the files for you to wget, or you can select to send the files on the projection on the web. And this will redirect you to the processing page where we've got interfaces for this. So the first thing we've added since we talked about this last is templates. A lot of people were a little overwhelmed with how many options you get to choose when you're setting up your projection and things. So we've tried to do some templates to help you with all the options. So you can choose from jobs that you've run in the past and reuse those options, or you can use templates that we've set up in the USGS. There's GIS ones. Each of these right now mostly just gives you polar and a couple other options. If you're working with GIS, it mostly goes to GeoTip, which is the file format that works best there. For this example, we'll go ahead and do something with the web as our output, or something that will display inside the browser. What you have is, if you know somebody else and they've sent you one of these job keys, you can paste that in and use their job settings to simplify things. This can really come in handy when you got a lot of jobs or a lot of files you want to process, the settings over and over again without having to worry about what changed or what's different. So we'll go back to, once you get here, you'll get a list of the files you selected from Pilot. You can name your job, which this becomes helpful when you're going back looking at those old jobs to figure out what settings you want, what's going on. You can see the image options. This is a pretty simple image. If there's multi-band, you can select the bands and which ones you want for RGB. This has gone ahead and set the projection for us for planimetric. We're not going to bother clipping because it's just the one image. It's got the download format to be a thing, so that'll be easy to open in the browser. We just go ahead and add the job. Now, part of what happened there is we'll get an email sent to us. Not right away. Let's go ahead and go to monitor that job. This page will have details about your job as it runs, when it's been queued, started, finished. On here, you'll be able to download individual links and a zip file of all the files together. There we go. So here's a link so you can track it. You'll also get a notice when your files are getting ready to be removed. You get 2 weeks once the job is completed and all the files have been created. Go back to the PowerPoint for a moment. Similar to the map projection on the web, the Map of Planet 2 service lets you work with derived products, so mosaics and other products that are stored on Astropedia, which is part of the astrogeology website. Again, you can do map projection, clipping boundaries. This also includes the FX function from ISIS. We've got some canned built in there depending upon the mosaic that you're looking at. All the services are free. We do need you to sign up for an account so that email and some other contact information when your products are ready. Yeah, pilot to search for EDR data for projecting individually, or just go to the astrogeology website to look for the derived map 2 products. This is a shortcut to go directly to the tools page from Map of Planet 2. And so this will actually give you planets and then the list of products that are available for processing on those. These products have been eligible for processing through the web service. Individual pages within Astropedia give you a reference of the image. You can download a small sample as a JPEG. A lot of the originals were switching to geotips. They were originally in there as ISIS cubes, which were difficult to use. There's a full list of details and backgrounds for the metadata on the product. Right here is the process button to send the product over to Map of Planet 2 and go ahead and do your processing on it. So for this one, just really quickly, go through. Again, you'll see your product there. The name is set by the job, but you can set it to be whatever you want. So this one is a multi-band image. Okay. You can choose to use a single band. You can choose which filter you want to be your red, green, and blue. All bands for this colorized image. Projections set already by the template we used. But for Map of Planet 2, you do need to still go in and set your clipping boundary, which may be more than you really want. Go ahead and click there. As you're going along and choosing your options, we try to guess at what the size of your file is going to be. So if you want to keep an eye down here as you're going, if you set the resolution too high or some file formats, you might be looking at a very long download. There's a few more stretch options available in Map of Planet 2, and we're working on adding more of those in the near future. And add that job too. All right, let's see if we go back to this one. Progress. People are checking out the services this week, and so we've got the there. All right. As we talked about on the data page, you get some details about the product, download links for the raw product or the whole product, or and the link to process. There's a little more detail on the templates that we talked about, and going through the different options that we basically demoed already. It's job name. With one of the FX functions that were available for a mosaic product. And those are going to depend on the product more than anything else. We're trying to make sure those functions will work well, so we're limiting them to products we know that work well with. Again, the projection, you can choose from actually supported by ISIS. You can set your clipping area. You can change what longitude, latitude, domain, direction, comfortable with. And then the supported download formats are ISIS3 cubes, in which case we skip the GDAL processing, GeoJPEGs, GeoTIFFs, PES, JPEGs, PNGs. That is done as a final step using GDAL Translate. You can track the progress on the listing page from the AstroCloud website. Hold that up. Okay. All right. Just really quickly look at what this shows. I'm an admin, so it'll just take it a second to load and clear out to just show the jobs I have running right now. Okay. So these two jobs are submitted, but they're not yet running. This is one I ran a little while ago, and the files are ready, so we'll go ahead and check that out. Once your job's done, different timestamps will be registered, so you can see that it's, and you'll get a zip archive of all the files that were created. Process log. And this is kind of nice if you want to learn this. This gives you the different commands that were run to create the product that you ordered through the website. You can also get to individual download links for the files that you have processed. Just don't know what they'll open here. We just talked about the details on that page to keep track of your jobs and get to the files that were created. This project was originally funded by NASA's PTNG cartography program. It's now supported by the PDS imaging node. That's about all I have.
Questions?
So it was good timing for me to come in, I see, on the last slide. Yeah, sorry, I missed it.
So I guess we, as a question, we do keep metrics, but I don't know if we publish those.
I took the slide out because I want to make this available as a how-to on the website.
Okay.
But yeah, on a monthly basis, it kind of varies. If it's LPSC, we're in the multiple terabytes of downloads. Everybody getting figures and playing with things and doing that kind of stuff. Typically, I think the combined download for a typical month between the two services is about 2 terabytes.
It's actually, it's funny you pointed out LPSC. I think the increase in terabyte load was 10 times during March, just to show you how much people grab data for LPSC. Pretty hilarious. All right. How's the PDS wrapping up? Is that?
They're done. Most people have left.
They're done. Okay. So thank you all. I think we had a good day. A lot of demos, a lot of presentations. We do have the kind of happy hour group social. If you want to join us at the Root Public House, it's 2 blocks north and a little bit to the right over here. It's on the rooftop. Just perhaps you've gone too far. So just look for that Root Public House.
On San Francisco, the address is 101 South San Francisco.
101 South San Francisco.
Yeah.
That's it for today. Tomorrow, I forget what time we start.
8:30.
8:30 again. So that is kind of a summary of this idea that we've been talking about a lot, spatial data infrastructure, how that fits in, how we might coordinate these tools. We saw a lot of interesting tools today. I think one of the first comments Ray made this morning was, wow, I'm not sure what tool to use when. Should we try to get a registry? Should we try to do, I think those are really good ideas. Hopefully we can talk about that tomorrow. Thanks again for being here. I hope you join us tomorrow. If not, thanks for coming. We'll see you at the rooftop.
Thank you. You did it already?
Yeah, I just put everything on there.
Okay,
We haven't figured out.
Thank you very much.
It's a good backup.
Yeah, exactly. Thank you, Scott. I'm sorry I missed it.
No, it's fine.
Yeah, it's not that working so much. Anyway. Yeah, no. Well, and they charge us for every little thing, so we are reluctant to ask for more than that because it would be even more expensive. Well, the thing she takes off of our hands is the negotiation with the hotel.
Right.
And, yeah, and the food, which we can't do ourselves.
Yeah.
So, to me, that's huge, but yeah, but in terms of paying attention. Yeah.
Yeah, no, we